Okay, so let's get started. Today's lecture will be about network security. But before we start, you probably noticed this already, but just to make sure, there's a change of schedule that actually was done a week or so ago, and it's basically that the exercise and lectures this week had changed spots almost. So on Thursday there will be the last exercise, and on Friday will be the last lecture. But there's a little bit of a strange time here, so it's between 2 and 4. Okay, so the reason for this is that apparently there is a course evaluation meeting between 1 and 2 for some people in the class, possibly none in the class actually, but so I was not allowed to do it like this otherwise. Anyways, so that's what it's going to be. Last time we talked about Wi-Fi, so a quick recap on that. The IEEE standard 802.11, this is also known as Wi-Fi. It specifies the MAC and PHY layers. There are many variations of PHY layers and MAC layers and so forth. The most common MAC is called DCF, and this is the one which is used heavily. And it uses carrier sense multiple access with collision avoidance. So basically what happens is we listen to the medium if we have a frame to transmit during a specific time called diffs. FS stands for IFS stands for interframe space. D here stands for the DCF interframe spacing. And if it's idle, we transmit. If it's not idle, then okay, so if the medium is busy or after a completed frame transmission, or if we detect a collision, then we trigger back off. So back off is triggered by one out of 3 things: a busy medium, that we have transmitted the frame and we have completed this, or we have detected the collision. That is, we are transmitting something but we don't get an ACK in time. Then we're going to back off. And we back off a number of slots, and the number of slots we back off is randomly chosen every time within this contention window. And this back off counter is then counted down while the medium is idle for a slot time, and then we pause this down countdown, or the back off counter, if the medium is busy, and then once we have eventually back down to 0, then we transmit. So this is the collision avoidance thing in Wi-Fi. So data frames are acknowledged and transmitted if needed after the appropriate back off. Repeated retransmissions cause contention window to grow exponentially to reduce the probability of future collisions. This is good, but it comes at the expense of increased delays. Then we talked a little bit about this RTS-CTS handshake, which is optionally used. Optional means that we don't have to use RTS-CTS. But if we do that, the objective with this is to reduce the number of problems due to the hidden terminal. And that is when a hidden terminal occurs when a station is sensing the medium and there is an ongoing frame transmission, but this is not detected. Okay, so there is a transmission which is hidden to the node which is doing carrier sensing. Okay, so we talked about that in some details, and RTS-CTS is a way of reducing that problem, not completely eliminating, but reducing it. Carrier sensing, there are 2 versions of it, 2 options. One is that we do physical carrier sensing that basically listens to the channel and then listen to the power level. And if the power level is strong, then we say that the channel is busy. There's something called virtual carrier sensing also, is that when you, in the frames that are transmitted, there is a field that tells us how long it would take for that frame to be transmitted and the acknowledgement to be received. and then we can wait the appropriate time. Yeah, so channel is busy, that either virtual carrier sensing or physical carrier sensing says that the channel is busy. Hidden terminal, we talked about that. That's a station whose transmission is not detected when sensing channel. Something called exposed terminal, that's a station whose transmission is unnecessarily blocked by carrier sensing. And if you go back to the slides, you see what they imply. All right. But today we will talk about network security. So it's sort of course, related to everything that we've done in the course, that security is increasingly more important. And there are many aspects to this. So this learning outcomes for security are listed here. They are relatively new. I think they've been in the course now for 3 years maybe. So you will see them on exams, 2 or 3 years back in time. You won't see them further back in time because then they were not part of the course. But I can almost guarantee that something about security will show up on the exam. So it's because it's not part of the project, it's not part of anything else. So the exam is the only time where we examine these learning outcomes. So today will be on the exam, something. Security is very important. Of course, we're only scratching the surface here. There are courses in network security and many other types of security here at Chalmers that you can take if you're interested in this field. But this is something that I think everyone should know about that's dealing with the communications. What we will talk about today. Okay, so to be specific, what we will talk about security today falls into the class of computational security. Okay, so when further on we would say it's impossible to break a crypto, it's impossible to get this knowledge and so forth. What we actually mean by that is that it's not possible with feasible cost, with reasonable computational resources. So actually all the cryptography that we talk about today are in principle breakable if you have enough computational resources. But if these computational resources are all the supercomputers on Earth computing to the end of the universe or until the sun extinguishes, then it really doesn't matter whether it is possible or not, right? So it's in principle impossible. It could be possible to break crypto also if some great innovation is done in mathematics, which is unlikely, or if some specific hardware, something called quantum computers, actually be realized. Then some of the cryptography that we talk about today will be broken. And as you know, there are some people here at Chalmers trying to build a quantum computer. And if they do, they will then endanger the internet as we see it today. So I'm not so sure if I want that research to be, successful, not in the short term at least. Yeah. But anyway, so this computational security, I want to stress that it relies on the assumption that certain mathematical problems are hard to solve. These assumptions are well founded. I mean, they're not just picked out of thin air, but they are still assumptions. And cryptographic schemes that we will talk about are constantly being analyzed for weaknesses. And weaknesses are discovered on a regular basis. And then it could be an implementation problem, or it could be some flaw in the way the system is built up. And then one has to patch it, basically, to fix it. So schemes that are proven to be deficient in some respect are either patched or taken out of service. And I think one classic example of this is the early version of security in Wi-Fi called WEP, which is now seen as completely broken, so it should not be used. What is interesting is that the current scheme, which is recommended, WPA2, last year, I think, proven to have some weaknesses in it. So it's also getting updated. Now, these weaknesses could be big or small, right? but for sure it was a weakness that one was not aware of, and one now tries to do something about that. It's not on the scale that you should stop using Wi-Fi. At least, I mean, if you're in the military, maybe you would do this, but I mean, for us, I think I don't think even the military should care so much about this. But anyways, so let's talk a little bit about security and what that means. There is several things that one can mean with security. Is confidentiality, integrity, and authenticity. So we'll go through them. But I think the most classical example is secrecy or confidentiality. So what we have here is we have two honest actors, Alice and Bob. So Alice and Bob wants to communicate. Okay? And they're communicating over a channel where there is possibly an evil actor here, Eve. Okay, or E for eavesdropper, which means that somebody that listens in to the communication here, a person in the middle. And the objective is to find a way so Alice and Bob can communicate without Eve knowing what they're talking about. Okay, so that's a classical cryptographic problems, I would say. So to introduce some terminology here, Alice has some message, M here, which is also known as the plain text. So this could be, you know, a file, it could be a few characters, it could be a different size. But there is some message here. And this message Alice would like to send to Bob in a confidential matter. So what Alice does then is to take this message and encrypt it. And encryption is done through an algorithm with the help of a secret key, K. So K here is a bit sequence of some length, maybe 128 to 256 bits or something like this. And this key, this secret key, is something, a shared secret between Alice and Bob. So Alice and Bob, they know the value of the key. They have agreed upon what the key is. So there's been some key generation process to generate because most often this key, the best key we can use is a completely random sequence of bits. Independent, equally likely bits. Question?
Does it have to be connection-oriented communication then? If there's a key that they have agreed upon to use?
That's a good question. So so the question was whether this communication here needs to be connection-oriented. In a way, right? Because one has to share this initial key somehow. But this could have been done when the devices were manufactured or when they met somehow and exchanged this key. So it could be quite a long time before we actually did the communication. We'll talk a little bit more about that in a second, because this key distribution, key generation is not very tricky, right? But key distribution is a big problem. As we will see. But if we assume that this is here, okay, and we assume that this has been secure, which means that Eve has not knowledge of K here. Then, in the encryption mechanism here, Alice takes her message M and the secret key K and feed that through some algorithm that spits out a ciphertext. And the ciphertext is a bunch of bits, okay, and these bits are then transmitted over the channel. Eve observes C, okay, so Eve can listen to C, know every bit in C, okay, and then one would like to make it impossible to Eve to say something about M, okay, and say something about M means that not decoding a single bit of it. Okay, or even less. It should say exactly nothing about M. That's what the goal here. Okay, anyways, the ciphertext is then received by Bob, and Bob feeds this through a decrypting algorithm, some algorithm here with the secret key that Bob and Alice has shared, and the ciphertext, and out pops the message here. So the decoding algorithm, the decryption algorithm, is the inverse of the encoding algorithm if they are fed with the same key. Now, so what does Eve know here in this setup? Eve knows the ciphertext. She knows about the encryption and decryption algorithms, okay? But she knows nothing about the key, K. So that's the setup. So this is an important principle. Actually, there is a principle called Kerckhoffs's principle, and it's from 1883. So he didn't exactly say it like this, but this is what he meant. He said that a crypto system should be secure even if everything about the system except the key is public knowledge. Okay. So that's the modern way of designing things, that we don't keep the encryption algorithm secret. The source code of this could be known and is known. It's distributed freely, right? Also, the decryption algorithm as such is also well known. It's known exactly how it works. Okay. The only thing which is secret is the key. Okay. So a common mistake among amateurs is that one figures out, oh, I know this fancy algorithm that I think will spit out a secret garbled text, right? This is what I will use in my secure system. The problem with this is that when this encryption algorithm leaks, then the whole system is broken. Okay. However, if one has a commonly known encryption algorithm and decryption algorithm and keep the key secret, then this scheme is broken when the key leaks. Okay, but then I change key, and then I'm operational again. Right. So this is a very commonly used principle, right? We don't keep things about the encryption and decryption algorithm secret. We only keep the keys secret. Of course, nothing prevents you from doing both, right? But you should never rely on the secrecy of your encryption decryption algorithm for making things safe. Any questions so far? All right. So let's talk about a very good scheme, which is called the one-time pad. And this is actually known to be what's known as a perfectly secure system. All right, so let's go through that. So suppose that the message is a sequence of bits and that we have n bits in it. Then we pick a key, k, which is to be a random n-bit sequence. Okay, so with random here, we mean independent, equally likely bits. So we basically run a random experiment, and the output of this will be k bits. And this we set to our key. And this is then shared between Alice and Bob. So the key generation is basically to draw n random bits. Okay, and then these are shared between Alice and Bob. So this is the to create the key and then to distribute the key. Then encryption is this. It's very, very simple. We basically take the message and we do XOR with the key. And that's our ciphertext. Decryption is equally simple. We take the ciphertext and we take the XOR with the key. Why does this work? Well, it's because the ciphertext is m plus k. So m plus k becomes m plus k is what? It's equal to 0. I mean, it's XOR, right? So all the ones become, yeah. So it becomes 0. So it's m plus 0, and m plus 0 is m. So this works, right? So encoding, decoding is super, super simple. So the one-time pad is secure if the key is never used. One can prove this mathematically. I will sketch a proof in a second. Okay. So why is this not used always? Well, the answer is on the slide. And the main problem with this is that we need a unique secret key to be shared among all the pairs of communication parties, and the key needs to have the same length as the plain text. So we need to do that for every new message. And if we think about it, we need to share the keys securely in order to share the message securely. But the key contains as many bits as the message. So what did we really gain here? Right? But anyways, the one-time pad is sometimes used, and it's an example of what's something called a symmetric cryptography. That means when Alice and Bob share the same key. Or symmetric cryptography is when the encoding and encryption and decryption is using the same key. You will see when this is not the case in a later example. Symmetric cryptography is also called private key cryptography. And an example of a practical scheme that does this is something called AES, stands for Advanced Encryption Standard. And this is a pretty good scheme. That's what's recommended to be used today. If you want to use symmetric cryptography, AES is your best bet until we find something better. But let's go through a small sketch of a proof that shows why the one-time pad is perfect. Okay, and with a very small example here. So we have the message. It should be a number of bits. Okay, so this is 0100, for instance. Okay, so this message is generated by Alice. We can think of this as, you know, something that Alice has generated. We don't know the statistics behind this. We don't know the probability that the first bit would be a 0, the second bit being a 1, or something like that. But we can assume that there is some type of distribution of these bits. It's just that we don't know that. Okay? And we don't want to tailor the encryption scheme to be reliant on the statistics of the message. We want that to be safe in all respects. Okay, so what we do then is that we generate the key. Okay, then we run our key generation algorithm to generate 4 bits. Okay, we need 1, 2, 3, 4 bits, and these should be random somehow. Or they should be random, equally likely ones and zeros. So maybe it's 1, 1, 0, 1, like this. And then the ciphertext is just the XOR between these two things. So it's 1, 0, 0, 1, like this. Okay. So the key here should be chosen randomly. So equally likely independent bits. Okay. So if we call the first bit here in the ciphertext, okay. So remember that Eve, the bad person here, learns about the ciphertext, and the objective of Eve is to try to figure out something about the message. Okay. So let's see what Eve can deduce from this. So for instance, what is the probability from Eve's perspective that the first bit is 1? Okay, so what does that mean? Well, it means that the probability that C1 is equal to 1 means that the first bit in the message and the first bit in the key are different. Right, they're either 0, 1, 1, 0. Okay. So it's the probability that M1 plus K is equal to 1, which is the probability that M1 is 1 and K1 is 0, plus the probability that M1 is equal to 0 and K1 is equal to 1. Right. These are mutually exclusive events, so we can just add the probabilities for these. Okay, so can we say something about this? Anything further? Well, we can. So let's look at this probability first, and then condition on the value of M1. Okay, so we can write this joint probability as the probability that K1 is equal to 0, given that M1 is equal to 1, and then times the probability that M1 is equal to 1. Okay. So this is the joint probability of K being equal to 0, K1 is equal to 0 and M1 equal to 1. Okay. And we can write the second probability in the same fashion. It's the probability that K1 is equal to 1 given that M1 is equal to 0 times the probability that M1 is equal to 0. Okay. And now we're almost done. So, what is the probability that the first bit in the key is 0 given that the first bit in the message is a 1? What do you think?
Isn't the bit in the key and the bit in the message independent of each other?
Exactly, it's a good question. So the bits in the message and the key are independent of each other. Correct.
Then isn't it just 0.5?
Exactly. So this, the key does not depend on the message. So this is equal to the probability that K1 is equal to 0, right? It doesn't depend on the message. We generate the key independent of the message. So this is simply 1/2. And the same argument is that the probability that K1 is equal to 1 given that the message bit is 0 is also equal to the probability that K1 is equal to 1. So this is equal to 1/2. Okay. So what is then the whole thing? Well, it's 1/2 times the probability that M1 is equal to 1, plus the probability that M1 is equal to 0. And what is this?
Well, isn't that just equal to 0.5 altogether?
Yeah, exactly. So here's the probability that M1 is equal to 1 plus the probability that is 0. And then we have, it's either 1 or 0, right? We don't know the individual probabilities, but when we add them up, it's 1. Okay, so this is equal to 1/2. Okay, so from the perspective of Eve, she will see a sequence of bits which are equally likely 1s or 0s, regardless of what the message was. So Eve is clueless. She has no chance by observing C to figure out what M is. However, Bob, who knows the key, can recover M perfectly. Right. So that's the one-time pad, right? It relies on this beautiful, this interesting property that if we take a sequence of bits and we do XOR with a completely random sequence of bits, we get a completely random sequence of bits. So we can completely hide the message by doing this. Okay. Yes, question?
Is there a problem that we know the length of the original message?
Okay, so the question is there a problem that we know the length of the original messages? And yes, there is, right? So suppose we have a communication and you would like to say, okay, should I buy or should I do something? Should I fire my nuclear missile, right? And then you get the answer and you get either 2 bits or 3 bits? Okay, so that's the answer. So depending on which language, you would know that this means ja and this means nay, or maybe this is yes and this is no. So you need to know the language, right? But you can deduce from the length of the message something important in many cases. So in a complete scheme, what you would like to do is also to hide the length of the message. And you could do that by padding out to a specific length, for instance. There are various ways to do this. Okay, so the one-time pad is perfect, so why don't we use it? Well, the main problem is the key distribution problem, that the key needs to be transmitted securely to somebody else, but wasn't that exactly the problem we had from the beginning, right? So it seems like this we didn't gain so much. But anyways, what one can do, as I said earlier, is that Alice and Bob can meet at some previous time and exchange this key and keep this key while for a long time until they're separated, and then use the key once to communicate. And then they have to meet again to share this key and so forth. Another way to do that is to send the key with a courier. So this was actually used during the Cold War. There was a hotline between Washington and Moscow, a telephone which was encrypted, and the key to this was shared between the Moscow and Washington with the aid of a courier. So one created a very long key, printed out that on computer paper, put it into a briefcase, handcuffed it to a courier, you know, you've seen the movies, and then that courier put on a plane, and then, you know, and that's how you sent the key, right? So it was not maybe so urgently quick to do this key, but when you're about to press a nuclear warhead button, whatever, then you can lift the hook and then you can talk to each other securely for some time until you need a new key. Okay, but anyways, this is typically impractical, so we would like not to do this. So what can we do instead? Well, one can use this advanced encryption standard, and this is not perfectly secure in the sense of a one-time pad, but it's secure in the sense that it is impossible to decrypt this if the key length is long enough, right? In the sense that it will be very expensive to and possibly impossible to do this with the computational resources to our Okay, so let's now talk about the other main family of encryption schemes, which are called asymmetric cryptography or public key cryptography. And here the thing is that every user has two keys, a private key, which is secret, call it SK, and a public key, PK. So, yeah. And if we want to use this for secrecy, then we do encryption with one of the keys, namely with, somewhat unintuitively perhaps, with the public key, okay? And the public key is something which is known to everyone. Okay, so we can put out the public key on on a website or on a bulletin board or, on our business card or whatnot. It's something that you don't care about. You can just spread it, right? The decryption, however, is done with the private key. Okay, and the private key is actually, this is the secret you really would like to keep secret. So if I'm Bob, I have a secret key and a public key. And the secret key I really want to keep to myself, but the public key I would like to spread it, or it doesn't matter if I spread it or not. But for sure, it does not need to be secret. Okay, and this means that since encryption is done with the public key, that means that everyone, including Alice, who wants to communicate with Bob can use Bob's public key to encrypt the plaintext. So everyone can do encryption, right? But the only person that can do decryption is Bob. Because decryption, you need Bob's private key, his secret key. Okay. So in a setup like this, we have Bob. He has a secret key and a public key. Alice knows Bob's public key. She knows it, Eve knows it, everyone knows it. Okay? So the public key is used to encrypt the message from Alice to Bob into ciphertext C. It's decrypted by Bob using Bob's secret key. Okay? Only Bob can decrypt, because only Bob knows his secret key. So it turns out that one can design this encryption and decryption schemes together with how we generate these pairs of keys in a way to make it impossible for Eve by looking at C to figure out what M is, even though that Eve knows the public key of Bob. So any questions on this? So first time one sees this is a little bit mysterious, right? But this is but this paradigm to have what's called asymmetric cryptography or public key cryptography, that we have a key pair. We have two keys, one which is used for encryption and one for decryption. Turns out to be very nice features with this, as we will see in a second. Okay. So a few things about public key cryptography is that the public key is not a secret. That's in the name of it, right? So anyone can encrypt, also people that Bob have never met. And this is a great thing, right? Because suppose Bob is a website, right? Maybe Amazon or something like this. And Amazon would like Amazon's customers to be able to communicate with Amazon with secrecy, right? Which is possible, right? Because Amazon could put up its public key in the public domain. So everybody who wants to communicate with Amazon can use that public key to encrypt their messages and send to Amazon, right? So Amazon never met this new customer, but they can still communicate securely. So that's a great advantage. The secret key, however, is a secret, right? That should be kept secret. Because if it's not a secret, then other people can also decrypt, which is defeats the purpose of this, right? Now, key distribution for this reason is easier, right? Because we don't have to have a secure channel to share the public key. You can do that in the open, okay? So it's easier than private key encryption, but we will see a little bit later that it's certainly not a piece of cake. There are some problems with this also. Okay. So what is the main drawback with this? Why don't we always use public key cryptography? And that has to do with the computational complexity of the encryption and decryption algorithm. It's about 100 to 1,000 times more computationally expensive to do the encryption and decryption for this. And this is the reason why, for instance, if you have battery-powered devices, Internet of Things, and so forth, these cryptography is expensive, right? It might not fit your power budget or your device cost budget. Okay, so it's expensive. So a practical solution for this is the following: that Alice and Bob use public key cryptography to share a key. A private for a symmetric cryptography, okay, and this is sometimes called a session key, and then Alice and Bob use this private key cryptography, maybe AES or one-time pad. One-time pad is not really used in this, but AES for sure. And then with this session key, and then they communicate large volumes of data until they're done, and then they throw away the session key until they connect next time. So maybe this answers your question a little bit about connection-oriented and so forth. I mean, this is a connection-oriented type of thing. You start by contacting each other using public key cryptography, and then you set up a few things, share a key, and then you run your communication session until you're done, and then you shut everything down and you throw away the session key. Okay. Yes. Any questions?
Is there
Yeah,
the
yeah.
secret key, right? But then you would have to
Yeah.
find a way to actually find the message.
Yeah. So the question is, can one, by just inspecting C and perhaps also knowing the public key, can we somehow deduce what the secret key is here? And not if it's well designed. I mean, one way one could do here is, for instance, since we know the public key and we know the encryption here, we can test all possible messages until we get the cipher text. Once we know the cipher text and the public key, then one can deduce the secret key. Okay, so there is a way of doing that. It's just that it's computationally impossible to do this, or thought to be computationally impossible. So yes, mathematically, but in practice, no. So that's computational security, right? And the most common way to do this now on the internet will be broken by quantum computers. So that's not so nice. Okay, then we need to figure out that there are other ways one could do this, right? But so not all internet is not lost, hopefully, or I don't know. Anyways, I think it's. How about if we take 15 minutes here and then go over to the integrity and authenticity?